Day 2 of the video notes for 4.1 and 4.3 goes through a bunch of example problems. We're going to graph f of x equals negative 3x to the fifth plus 5x to the third without a calculator, just by understanding what the derivatives and second derivatives give us. So if we take a look, the first thing that we want to do is we want to look at the function. So the function, when it's equal to 0, is at negative and positive square root of 5/3, as well as 0. So if we take a look at that on the graph, that will look like a 0 value of the function here, and then a little bit bigger than 1 and a little bit less than -1. So that is how we will graph the zeros of that function. Now we're going to take a look at the derivative. And so when we look at the derivative of the function, f prime of x, we just take the derivative, negative 15x to the fourth plus 15x squared. I'll factor out a negative 15x squared. We set it equal to 0. And what ends up happening is we get x is 0 at, or the derivative function is 0 at 0, 1, and -1. So if I take a look at a sign chart for f prime of x, and I substitute in values to the left of -1, between -1 and 0, between 0 and 1, and to the right of 1, I get these values in the derivative, which means that my function is decreasing to the left of -1 and to the right of +1 and increasing in between. While at 0, we're neither increasing nor decreasing, but we kind of go from increasing to increasing again. And so let's take a look at what that would look like graphically. So if we are looking at this, we're going to have what appears to be a local minimum at x equals -1, because we're going from decreasing to increasing, and a local maximum at x equals 1, because we're going from increasing to decreasing. So if we take a look at that, and I substitute in values at -1 and 1 into my original function, what I find is that f of 1 equals 2 and f of -1 equals -2. And I'm going to want to put those points on the graph, because those are going to be max and mins of my function. So I'll want to put those points on the graph, and then we'll kind of figure out what everything else does after we take a look at the second derivative. So if I'm taking a look at the second derivative, I take the second derivative, so I just go negative 60x cubed plus 30x. I factor out a negative 30x, and I solve for x, and I get 0, negative root 1/2, and positive root 1/2. I'm not simplifying the square root, so I'm sorry about that. So if I take a look at a sign chart, I get plus minus plus minus after I substitute in some values, and I'm just kind of saving some time by doing that ahead of time. So that means my function is concave up to the left of negative 1/2 and between 0, I'm sorry, negative root 1/2, and between 0 and root 1/2, and then it's concave down otherwise. So if I look at how this might look graphically, I'm going to look at what the values of my change in concavity are going to be. So at negative root 1/2, I'm going to change concavity. So that'll probably be somewhere around here. I will also change concavity at 0, and I will change concavity at around root 1/2. So what's likely to happen in this graph is I'm going to, well, what's definitely going to happen in this graph based on what I have is it is decreasing and concave up until -1. Then it starts increasing and concave up until this blue dot. Then it starts to stay increasing, but it's concave down. Then at the next blue dot, it stays increasing. Notice it is increasing all the way from -1 to 1, with the exception of 0, where it's neither increasing nor decreasing. So it kind of probably has um, a vertical tangent line or something along those lines at that point. Then it starts to be increasing and concave up until the next blue dot, where it is increasing and concave down again. And then at the red dot, at x equals 1, it starts to decrease while being concave down still. So that is essentially what my graph is going to look like. If I take a look at the the values of these absolute and relative mins and inflection points, notice that I have no absolute min or maxes, because if I look at the graph, it goes off to positive infinity to the left and negative infinity to the right. So there's no absolute min or maxes. Um, I'm only guaranteed to have absolute min or maxes in situations where I have a closed interval. But since this interval goes off to negative, since the domain is negative infinity to infinity, I can't guarantee any absolutes. And in this case, I don't have any absolutes. Whereas if the function was a parabola or something, I could have an absolute min. The relative mins, or the relative min, is at -1, -2, which I saw since I had a critical point that had a sign change at -1. And then the relative max happened at +1. There was a sign change there. And then I had some inflection points as well at 0, 0, and at plus or minus √1/2. And then I found the y values of those on the calculator. So I kind of cheated on that. But that would be where the inflection points are. Let's analyze a second one completely. So let's take a look at f of x equals x times square root of 16 minus x squared. I'm going to go through this one pretty quick as well. It is important to check the domain in this problem. Notice that the domain is going to be from -4 to 4. I can't substitute in any values that are less than -4 or greater than 4 into the square root part of the function. This is very important. Notice also that f of x equals 0 at 0, 4, and -4. So I can take 0, 4, and -4 and plot those points on the graph pretty quickly. I just sub in values that are going to make that equal to 0, and I figure that out right away. Now, if I take a look at the derivative, I'm going to rewrite f of x just to make taking the derivative easier. So I do the product rule, and then there's a chain rule with this part, the 16 minus x squared to the 1/2. Then I do a little bit of simplifying, and you can take the derivative on your own, but in the interest of time, I'm going to just tell you that the derivative is 16 minus 2x squared all over square root of 16 minus x squared. That will equal 0 when the numerator equals 0, which occurs at x squared equals 8. So x equals plus or minus √8. You can simplify the radical, but I'm not going to the rest of the problem. Also note that f prime of x does not exist at the endpoints, because if you substitute in 4 or -4, it makes the denominator 0. So that's something to keep in mind. Since the derivative does not exist, that actually would be a critical point under normal circumstances. But since the domain of the function ends at -4 to 4, I can't check for a sign change because there's nothing to the left or right of that within the actual function, and therefore it can't be a relative min or max at one of those points. It can be an absolute min or max because it's an endpoint, but we don't have to check for a relative min or max at those points because the domain ends. If the domain didn't end, we would have to check. So I make a sign chart. I substitute in values to the left of -√8, in between -√8 and √8, and to the right of √8, and that's what I get. So notice that f of x is decreasing, increasing, and decreasing at those values. And then when I substitute values in, to the function for those values, for negative root 8 and positive root 8, I figure out that f of negative root 8 equals negative 8, and f of root 8 equals 8. So I'm going to just make the scale go up by 2's on the y-axis and 1's on the x-axis. So at root 8, which is about 2-point stuff, I end up at 8. And at negative root 8, which is negative 2-point stuff, I end up at negative 8. So I know those are values that I'm going to have on my graph, and those are critical points. I can tell they're critical points because I'm changing from decreasing to increasing and increasing to decreasing. So those are going to be relative max and mins that I figure out when I substitute those values in a little bit later. Now, if I look at the second derivative takes a lot of calculation, and I'm skipping a lot of it because there's a lot of work, but it ends up being a quotient rule situation with a chain rule involved. So I end up with 2x times x squared minus 24 all over 16 minus x squared to the 3 halves. And I hope you just trust me on that one to make sure the video doesn't last forever. The derivative equals 0 when the numerator equals 0, so that occurs at 0 and plus or minus root 24. Notice that f double prime does not exist at the endpoints, and the same situation applies for f double prime as f prime earlier in the problem. Also note that x equals plus or minus root 24 is outside of our original domain of the function, so I don't even have to really worry about this part. If I take f double prime, 0 is a critical point of f double prime, and it changes from concave up to concave down. So at this point 0, I need to change from concave up to concave down. So what I have is I have a minimum value at this blue point, negative root 8, and the function is concave up all the way from negative 4 to 0. It then becomes concave down, and that ends up being kind of what my graph looks like. You can check it on Desmos to make sure it's actually accurate, but we are expected to be able to graph these things now by hand. If we look at the absolute min and maxes, notice this is a closed interval. So because the domain is closed, I absolutely have to have an absolute min and an absolute max since it's continuous and closed. They just so happen to be the same as the relative min and max points. I do have to check my endpoints, but since the endpoints are negative 4, 0, and 4, 0, those are definitely not greater than or less than my max or min values. So my absolutes are the same as my relatives. And then I had an inflection point at 0, 0. If I look at example 3, I already kind of have everything written out right now. So if I take a look at the sign chart that I'm given for f prime and f double prime, that can give me hints about f of x. So f of x is increasing in concave down between 0 and 1. It is decreasing in concave down between 1 and 2. And it is decreasing in concave down between 2 and 3. That I can get from the sign chart. Also notice it tells me what f is in these problems. And I must have a local max at 1, 2, because if you look, my function changes from increasing to decreasing there. Also note that x equals 2 is a critical point, but it's neither a max min nor point of inflection because I don't have a sign change in f prime or f double prime, even though my function derivative and second derivative do not exist there. Okay, since this is continuous on 0 to 3, f double prime being 0 could be relevant, but since all I know is information about 0 to 3, I don't know anything to the left of 0 or to the right of 3, that's not going to help me graph my function. So I'm going to sketch a graph of this, and I'm also going to answer the other questions. So after I sketch the graph, that may help me answer the questions, parts A and B, a little bit better. So if I take a look at this graph, I have a point at 0, 0. I have a point at 1, 2. I have a point at 2, 0. and I have a point at 3, -2. So those are points that I know are on the graph. Oops, my fault. 1, 2, 2, 0, and 3, -2. I know that I am increasing in concave down from 0 to 1. So increasing in concave down looks something like this. I am decreasing in concave down between 1 and 2. And then I have some sort of uh, weird situation. This makes sense because it looks like my tangent line appears to be going to 0 there. So I can kind of live with that. Um, this one probably should have a slightly different slope, but we'll kind of live with it for right now. And then I'm decreasing in concave down again. So my graph is going to look something like that. Okay, so this would be a representative graph of example 3. To answer part A, I have a max at 1, 2, my absolute max anyway, absolute extrema. And then my absolute min is at 3, -2 in this case. Part B tells me to find any points of inflection. I have no points of inflection because it's concave down the entire time with the exception of some endpoints and a does not exist, but I have no sign changes to indicate to me that there are any points of inflection. Example 4, if I take a look at example 4, I'm going to have the same stuff, but then my graph is going to have a slightly different look to it. If I'm looking, I have a decreasing slope from -4 to -3, an increasing slope from -3 to -2, an increasing slope that's constant. So the slope is 2 from -2 to 1. And then from 1 to 3, I have a decreasing constant slope of -3. Um, so one thing I forgot to point out is that this is continuous on -4 to 3. Then if I look at f double prime, it's concave up from -4 to -2 and linear from -2 until 3. And I know it's linear and not constant because f prime is non-zero from here until here. And so since f prime is non-zero, I do have a does not exist f prime at x equals 1. But all that means is that I have a critical point. Um, it, well, I could have a critical point, and actually I do have a critical point because notice my function changes from increasing to decreasing. F prime changes from positive to negative. So if I take a look at part C and sketch the graph, one thing that we notice here is that I do not have any indication of a y value for any of this. So I have to just pick a y value to start. So I'm going to pick a y value at, I'm going to pick -2, -2 to be a point on my graph. I don't have any reason to pick that y value. I'm just picking it. It tells me to sketch a possible graph, so that's what I'm going to do. Um, so what I will do is I know that the slope of my graph is constantly 2 from -2 until 1. So I'm going to go up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1. And so I end up with this line being on my graph. Then I have a slope of -3 when x is between 1 and 3. So down 3 over 1. That's not down 3. Sorry. Down 3 over 1, down 3 over 1. So I now have that point. Notice that it didn't matter where I started my graph. If I started my graph higher or lower or whatever, it wouldn't really matter. I have the same y value here and here at x equals -2 and x equals 3. That's because my slope being 2 going up this way and my slope being -3 going down this way is going to end up putting me in the same spots, since this has a length of 3 and this has a length of 2. So that's something to keep in mind. Now I'm going to take a look at the back part of the graph. My slope is changing and increasing from -3 to -2. My slope is never any bigger than 2. So as a result of this, since I'm concave up and I have the exact same amount of f prime of x in terms of slope below this axis and above this axis, it's going to start and end at the same y value. I'm going to be concave up and decreasing until I get to x equals -3, and then I'm concave up and increasing um, until x equals -2. So when I look at the graph, I can then answer the questions. The absolute extrema, uh, the absolute extrema of this value, or of this graph, this function, even though I don't know what the y values are, since I just picked some random y value to start, uh, and it shows up 3 times. I don't know what the y value of these absolute extrema are, but I do know where they exist. So there's an absolute minimum at x equals -3, which is a critical point of the graph, and it's a critical point of f of x, and f prime changes from negative to positive. So that means I know I'm going to at least have a local minimum. In this case, it's an absolute minimum. And then I have an absolute max at x equals 1. And then any points of inflection would be where I have changes of concavity. And in this case, there is one value of f double prime where I have a f double prime does not exist. That's at x equals -2. But notice it goes from concave up to f prime being 0. So that means it's not a sign change. So I have no points of inflection on this graph.